In this video, I'm going to be talking about the meaning of the covariance matrix and PCA. So the contents are twofold. Just like the title says, the first will be the meaning of the covariance matrix, and second will be the PCA. And for the meaning of the covariance matrix, I'm going to explain it in two views. First is a data structural view, and second is the mathematical view. And for the data structural view, I'm going to say that how the covariance matrix tells you how similar the variances of features are. And in mathematical view, I want to say that the covariance matrix does the linear transform or the sharing. And in PCA, we're going to find the meaning of the eigenvector and eigenvalue of the covariance matrix, and we'll see how the PCA works. So the meaning of the covariance matrix part 1, so the data structural meaning. So I just said that the covariance matrix tells you how similar the variances of features are. Okay, so let's think about a data matrix X, and this data matrix has samples in row and features in column. What does that mean? Let me just explain the features first. Let's say you have the data of height, as in how tall you are, and English score, like Spanish score, and like math score, science, something like that. And that is what the features mean. And in row, you can see that this is from like John's, this is from like David, something like that. So the first element in the first row and first column is the John's height, and the element in the first row in the second column is the John's English score. However, additionally, we have to subtract the mean of each feature. Then you get the X data matrix. Okay, this is important. So we demean the features, or we subtract the mean of each feature. That's how you get the X matrix. And I said that the X matrix is an M by D matrix. So it means I have collected the data from like N people, like number of samples is N, and the number of features are D. Okay, so I said here that this is a real valued matrix, but it doesn't really have to be. It can be a complex one, but in this video, let's just focus on the real valued ones. So now let's calculate the covariance matrix using X. So suppose we want to calculate the similarity of the variances of the features. So this matrix, I just said that we have to subtract the mean for each vectors. So itself, the X something means how much the features vary in terms of the average value. It doesn't really mean this variance. It's not the statistical meaning of the variance. It's not statistically like defined variance. Okay, like let's just say how change. We can say change. So to figure out the similarity, we need dot product, right? So and then one of the advantages you have if you have the advantage of the matrix is that you can calculate the dot product without much effort. So all you have to do is to multiply the X transpose in front of the X. So as you guys know, it'll give you the multiplication of the matrix, and it works like this. So the row of the first matrix and the column of the second matrix, and what you get is to multiply the element by element and add all of them. So that's that's the result of X transpose X, and like you can see, these are the elements means the dot product of each feature. And you can also see that this value, dot product of x2 and x1 is equal to dot product of x1 and x2. So it doesn't. It is the same. It gives you the same value if you swap the element in the dot product operator. So you can see that the X transpose X is symmetric matrix. Okay. And you can see that the number of the row is D, and the number of the column is D, as also D. So it's a D by D matrix. Okay. So the element in the ith row and jth column means the similarity of the variance of the, maybe I just said the change, similarity of change of ith feature and jth feature. However, there's a problem that it gets bigger. The element in the X transpose X get bigger as there are more samples. So we can solve the problem by divide every element by n, which gives us the result like this below. So this is the result. If we divide X transpose X by n, this is the definition of the covariance matrix, and the symbol is the large sigma. And in many textbooks, they say that you have to divide it by n minus 1, not n. That's because you are calculating the covariance from samples. So you're not calculating the what is that? The covariance from samples, not from the population. So you can divide it by n minus 1 as well, but as long as you have like lots of samples, like for example, like you have collected the data from like 1,000 people, then dividing it by 1,000 or 999, or like they give you almost similar result. So it doesn't really matter much. I just want to give you I just want to explain you the fundamental meaning of the covariance matrix. That's why I divide it by n, and you can find like many YouTube videos explaining about it. Anyway, so here if you divide it by n, that is the variance of the matrix. Okay, then this will tell you the covariance of the matrix. So it gives you what it tells you is that how similar the change of the x1 and x2 are how similar they are. So the ith row and jth column of the covariance matrix means the variance or the covariance of the ith and jth features. Okay? So that's it for the data structural meaning. And mathematical meaning, I want to say that mathematically it is a linear transform or shearing. And here let's think about a scatter plot of a pair of features. I'm going to briefly explain what the scatter plot is. And let's say the x-axis is an English score. And let's say the y-axis is a Spanish score. and we subtracted the mean of them. So let's say the mean was the 70, and the for Spanish the mean was like 60. Let's say this blue dot indicates the John's English and Spanish score. So it'd be like 71. The Spanish score was like 66. This is John. And you can see there are lots of like dots, and each dot represents the samples, and it's the score, the features, the scores for them. Okay, that's how you get this scatter plot, and this scatter plot shows you how similar two features are. If they're really similar, it'll be all the data will be on this line, right? If they're really similar, I mean, if they're same, then it'll be on this line, and if they're not really the same, then it'll be like scattered out of the center line. So this is what the covariance matrix gives you by this in this way. So we can think of the covariance matrix as a linear transform, like what the covariance matrix did is to stretch out the data point cloud into this direction and this direction. Of course, there's no change this time, no change in this direction, but there can be the directions if there are like some if they're really different, there'll be some changes in this direction as well. So you see that they are it was derived from the transforming the data, the original data into this by the transform, like this, the Shearing transform. So that was it for the mathematical meaning. And if you want to see more about it, you can find some like matrix as linear transform in many YouTube videos. You can find them. And I want to talk about, for the next topic, I want to talk about the PCA, and you have to figure out what the eigenvector and eigenvalues of the covariance matrix are. So the PCA helps you to reduce the dimension of the data while maintaining the structure of the data. What does that mean? Let's say we have collected like many of like 1,000 samples. The features are English score and Spanish score. Let's just say so. We have lots of data, and the data, each sample is represented on the dot of the 2D plane. And what does the reduced dimension of data means? Reducing the dimension of the data means you get the like overall score for the English and Spanish score. Like you can just call it like linguistic ability, like as in like overall score for that. Then what you will get is the one-dimensional feature data vector. Like this stays for St. John's, like David's, okay? And it gives you the overall score for it. How would you get that? The best way is to project all the data points onto this vector, right? Then you can maintain the structure of the data, and also you can get the a new score for the linguistic ability, and that's what PCA does. And if so, what is the best vector to project? to project. If you want to project that 2D scatter plot into 1D. I mean, you can just see here that some vector along this line could be the best. But how can you describe it by the best? Let's just project the data onto a vector 2, 1, and you can see here this is a 2, the length 2, and 1 here, and you can see what happens if I project the data onto this vector. You'll see, so from the 0 point here, the length of each vector, the data is represented by a vector, right? So length of each data from the origin gives you the overall score for that. But is this a best? No, I don't think so, because the variance, you can see the variance after like in the next video, you can see how can you tell it's a best or not? Because the variance of the projected data is not the biggest. You'll see that. And let's just say that we have projected the data onto this vector. What will happen? This is the result, and the variance of the result is 0.89, and the last one was 4.11. So we can say that the last one was a better, but how can you find the best? So the best vector is one that gives you the biggest variance after the projection. And then the best vector is a principal axis of the linear transform. You just saw that what the covariance matrix does is to transform the data point cloud here into like stretched the scatter plot like this. So when it does so, it transforms along this line and this line. These two lines, or the vectors, are called the principal axis. And this is the best vector to project if you want to reduce the data while maintaining the structure of the data. And the principal axis of this linear transform is called eigenvector. And the meaning of defining eigenvector is that after the linear transform, what vectors change their magnitude but not the direction. So this is what the equation says. So on this vector, you do some linear transform. Then, if the vector only changed the magnitude of it, then this vector is the eigenvector. Let's see here again. If there's a vector that changed the magnitude but not the direction during this transform, the vector must be on this principal axis, right? Or it could be on this axis, because this direction does not change the magnitude and direction also. Okay, so in order to get the biggest variance after projection, you have to project the data onto an eigenvector. And you can see here that this is the eigenvector of the linear transform, the covariance matrix. And you can see that after the projection, it gives you the biggest variance after the projection. Well, in this video, I didn't actually mathematically prove that the eigenvector, the projecting onto eigenvector will give you the biggest variance, but you can prove it by Lagrange multiplier, and you can find it in many textbooks, or you can find it on like many materials on the internet, so you can find it. But what I want to tell you what I want to tell you is the intuitive meaning of the PCA. So then what about the 3D data, and what about the n-dimensional data? Of course, in when it was 3D data, you would get like 3 eigenvectors, and if you have decided to project the data, like reduce the data into like 2 dimensions, then you can project the data onto a plane that 2 eigenvectors determine. So it'll give you it'll reduce the data into 3D data into 2D. I'm going to show it in MATLAB demonstration. And if it was n-dimensional data, and if you want to reduce the dimension of the data into k dimension, then you can also project the data onto a plane that the k eigenvectors determine, and it'll give you the reduced data in k dimension. Okay, that was for the PCA, and I'm going to give you a demonstration of the MATLAB in 3D PCA into 2D. Alright, this is my not YouTube, the MATLAB window. And you can see here this is the scatter plot, the 3D scatter plot of the data. You can see that this data looks like this. The scatter plot looks like this. And what you can see is that it was like inflated in this direction and this direction as well. But when you see it in this view, to the inflation upward was not that big. So what you can do is to project the data onto the plane, onto the disk. Let me show you this. So from here, it'll give you the projected data onto a plane. Let me show it again. From here to this, and you can see that they are like projected onto a plane. It was the original one, and it is the transformed one, like projected one. And if you project this data onto the 2D plane, this is what you get. So we had the data with the represented by 3 features, but what I just did is to present the data in 2D by reducing the dimension of the data, but also maintained the structure of the data as much as possible. Okay, so this is for it, and thank you, and hopefully it was helpful for you guys, and see you next time.